Hello, I'm Anna Mackay and this video is on the graphs of f, f dashed and f double dashed of x. Have your graphics calculators handy. So for this graph here, for this function, we need to draw the graphs of f dash and f double dashed on our calculators and hence find the coordinates and the nature of the inflection point. So let's go straight to our graphics calculators. So here's the function here on my screen, or it's written off to the side here on the right. So my suggestions are, make this your view window, just to speed up time here. I won't explain why. And for our y, -80 to 30 and a scale of 10. Okay, so we've got a lot to talk about here. We're in a minute going to draw the derivative without calculating it algebraically. So let's think about what we're expecting though. So in a function, when we have a maximum or a minimum, they're stationary points. So that's where you could draw a horizontal tangent. On the graph of the derivative, that's where the derivative is going to be equal to 0. And so graphically, that's an x-intercept. So what that means is where you see a maximum here, which is at -2, that's going to cut through the x-axis on the derivative graph. Same for this minimum. At 4, it's going to have an x-intercept at 4 because that's when it's equal to 0. Now let's think about which direction it's coming from though. This -2, is it going to come from above and cut through to below, or below and cut through to above? Well, that's when we look at the slope of this function here. So first of all, it's going uphill, and then it's going downhill to 4, and then uphill again. So if it's going uphill, that means it's in the positive region. So it means it's above the x-axis. So it's going to come from above into -2, and then it's a decreasing slope. So then we're in the negative region of the x-axis. And at 4, it's going to go from a decreasing slope to a positive, which means from the negative region up into the positive region. Let's graph that and see if it's right. So we're imagining a parabola that cuts at -2 and 4. How do you graph that without differentiating? Using your graphics calculator. So for Casio's, you push Option. Here is Calculate, F2, F1, and in here you need to hit F1 for the Y and tell it that you want it to differentiate Y1, and in that box there, don't push this X, use the button for X. There we go, and we'll graph that. And is it what we expected? Yes, it is. A parabola cutting through at -2 and 4. So we need the second derivative though for this point of inflection. I'm just going to turn off this graph for now so we can talk about it a bit more. It looks like there's going to be a change from concave down to concave up, somewhere maybe around this region here. So that's where it changes from, I guess, being sad to happy. And on the second derivative graph, that's going to change from being in the sad region, which is the negative region, so it's below the x-axis, up into the positive region. So because there's only one change of inflection, at 1, it's going to come from the negative region, because it's concave down, down is negative, to up. So that's actually going to be a straight line cutting through there. Let's have a look at that. So to differentiate using your calculator, we go Option, Calculate, second derivative this time, still of Y1 and our X over here, and let's have a look. Is that a straight line as we predicted? Yes, it is, cutting through there. Let's put on our first derivative graph again and just look at one extra feature that's happening. That. Now looking at the relationship between the first derivative and the second derivative as a pair. So if your first derivative graph, the red one, is the function you're interested in, the same properties apply. So as on the previous function that we talked about, a stationary point on a function, so this minimum here, on its derivative graph will be an x-intercept. And that's what's happening on the second derivative graph here, the green graph. On the red function, we go from a decreasing slope to an increasing slope. So that goes from the negative x region into, sorry, the negative y region into the positive y region. So it's cutting through the x-axis. So those same principles apply, that a stationary point on the function will be an x-intercept on its derivative. And the one extra point is that the stationary point on a function will, did I say stationary point? I mean a point of inflection on a function graph, so the blue one, will be a stationary point on its derivative. So that's what's happening on the red. And just think about this one. On the red graph, is there any change of inflection? No. So it goes from, it's just concave up the whole time. So that means there should be no stationary points on its derivative graph. And on green, is there a stationary point anywhere along there? No, there's not. So that ties in nicely to what we've been talking about. And to solve the problem, we were after the point of inflection. So you can't just do that shift trace on the blue graph. First of all, you need that x point there. So we'll just double check it. It's the minimum, if you like, on the second graph on y2. We'll hit enter, and that tells us that x is 1. You can barely see it there. So to find out the y coordinate, you sub x is 1 into the y1 graph, and it tells you that it's 1, negative 25. So that answers our first question. Going back to my other slides now. Oops. So here we are, just syncing up. So the answer to that question would be 1, negative 25. Moving on. So I want you to draw the graphs of the derivative and the second derivative for the function looking like this. Obviously using a ruler would be ideal. Just for time, I'm just going to speed this up a little. 1, negative 2. And the function that I'm interested in is looking like this. So this is our function. I want to draw the two derivatives, the first and second derivative. So when you come to do that, I suggest drawing a sine diagram. By the way, the maximum is at 1 here, even though it might not look like it. So let's draw sine diagrams. Sometimes a really handy thing is to draw them underneath. Now I haven't really left myself much room here, but I'll manage. So the first derivative graph. On the sine diagram, we put where you could draw a horizontal tangent. So I'd say there'd be 2 points, one here at 0 and one here at 1 for the first derivative. Now think about the slopes. So in this first section it's increasing uphill, so that's positive. Then it pauses, but it keeps going uphill again. So it's positive, positive, and then negative. Positive, positive, and then negative. Let's do the second sine diagram while we're here. The sine diagram of the second derivative refers to concavity. So concave up and concave down of the original function. So let's have a look here. If you were to extend that, that's a concave down section. Down is negative. Up until, so, and then it has a pause there. And so that is a point of inflection, again at 0. And it's negative there. Then this next section, it's part of a concave up. But it looks like somewhere in here there'd be another inflection point to then become concave down again. So let's call that point A, just for something to call it, because we've got no idea about its value because we don't have an equation. I'm just going to draw a line like that. So we know there's an inflection point, and in between it was positive and then it's negative. So we need to draw the two graphs. So thinking back to the first derivative, that when you're looking at this sine diagram, that's the equivalent of the x-axis for this graph. And so it's saying it's in the positive region, so positive y, and then it touches the x-axis and stays up in the positive y region, hence that plus, and then at 1 it cuts through the x-axis and goes into the negative region. So it's going to have a touch x-intercept at 0 and then cut back through at 1. Now the other significant part here is that its derivative graph, the second derivative, has a stationary point at A. So that means on the function above, which is the first derivative, that is going to be a max or a min. And going from positive to negative means it's a max. So what I'm going to draw you by air first of all, we have an x-intercept at 0 and 1 for the first derivative. It's going to come down and touch at 0, have a maximum somewhere, and then cut through at 1. And where is that somewhere going to be? It's somewhere in line with this A. So let's draw that, different colour. So I like to put on my x-intercepts first and sort of connect the dots. Now, it does not matter where that maximum is. We've got no idea about how high or how low that is, so it really doesn't matter. And then the second derivative graph is the derivative of the first derivative, or it's an indication of concavity for the first derivative. So 0 and A will be the x-intercepts on this second derivative graph. So that's where its graph is going to cut or touch the x-axis. So let's decide if it's going to touch or cut. It goes from the negative y region to the positive, then the negative again. So it's cutting through here, it's going negative to negative again. And so let's draw that in our final colour, cutting through here. I like to connect the dots and we draw a maximum there. And that maximum lines up with the point of inflection on the first derivative graph, if you can think about that. So there are two functions. There's a lot to take in there. This is a hard concept to get your head around. I do understand that. And one more. If you've been given the derivative graph, so I'm going to draw you one that looks like this, and I'm telling you at -3 and 5, I'm drawing a parabola. This is our first derivative function. I want you to draw the function. So sometimes it's really handy to draw a sign diagram. So this time round of this function, we've got -3 and 5. A sign diagram of a function is actually telling you where it is in relation to the x-axis. So if it's the sign diagram to match the graph. So here it is above, then below, then above. Above means positive, below, then above. And now you can interpret this sign diagram for the function one order above, which is f of x. And now these positives and negatives tell you about the slope of that function graph. So that function goes from increasing to decreasing to increasing again. So that means at -3, it changes from being increasing, so it stops, and then it becomes decreasing, and at 5, it somewhere turns and becomes increasing again. So that means we need a maximum here and a minimum here, but not necessarily on the axis. All we know is, let's say at -3, it goes from being increasing to decreasing. Whoa, hang on, let's draw that a touch better. Increasing to decreasing, and at 5 from decreasing to increasing. And the one extra piece that we've got is this minimum here will be a point of inflection on the function graph. So that means somewhere in a line with this, we would have a point of inflection. So let's approximate that for here and connect our dots very averagely. So that's our function. But by the same token, we could have that much lower down and the same shape. So you could have it with a maximum here, point of inflection there, and then a minimum at 5. And that would be just as acceptable because we've got no other information. So that's the end of this video. If you enjoyed it, give it a thumbs up and subscribe to the channel. And the next video in the series will be called Motion. Thank you.